Then let's start. Christian, can you share the slides on the screen? Yeah. Okay, welcome everyone to this second webinar in this series of our launch of the new VLCC products, where we are providing products annually for the thematic classes of forests, grassland, and croplands. In this webinar, this is the second one. As I said previously, on the 1st of October, we had the introductory webinar to the full product portfolio. And now we're diving deeper into the separate families, which we call it thematic webinars, where we will also look into certain use cases from presenters that I will introduce shortly. So just general introduction here in housekeeping, and then I will leave it to the presenters. This webinar is recorded as always, and it's for participants that cannot join us today, that we share it on the webpage after the fact, and so they can take part of it as well, what is presented. Also, please follow general courtesy rules. We have a Slido on this page where you can answer polls that will be presented during the webinar, and also to post questions that we will handle later in the Q&A session. So please feel free to post your questions there, and we will also highlight you on when there's new polls published. Yeah, I think that's all for this slide. As said, the QR code is here. You can also just enter the website and enter this code here, the 1337361. Next slide, please. And as I said, this is a series of webinars where we had the introduction to the whole portfolio last week, and now today we are going to dive deeper into the forest products and potential use cases, on actual use cases. And then on the 19th November, we will do the same for grasslands and the grassland mowing events and that product portfolio. And finally, on 10th of December, we will have a webinar on the novel products, the crop types and the cropping patterns, and look into more details of that portfolio, and also potential use cases or planned use cases of such products. Next slide, please. And then shortly, just now to introduce you to today's agenda. We're currently in the webinar introduction. My name is Ludwig Forslund. I'm the product owner here at the European Environment Agency for this product. And I'm also handling our other vegetation product, mainly the vegetation phenology and productivity, if that is familiar to you. And then after this slide, I will leave over to our project manager at GAF, Christian Siegert, who will introduce you to the VLCC, a bit of a reintroduction from last webinar on the full product portfolio, because all of these products are produced in one as one production system. He will also then dive a bit deeper into the different data sets within the tree cover and forest products, and also go through how to access the data once it's available. Then finally, he will leave the floor to Shaya, who is invited here for describing a use case. Shaya is working for the CBS Netherlands, the Central Bureau of Statistics, and describing how they are using these tree cover products for extracting statistics and measuring here ecosystem conditions. And then for our second use case, we have Stefano Salata from the Polytechnic University of Milan, who will be describing how they are designing urban green infrastructure using open source data, and among them the HRLs. Then, as I mentioned earlier, we will enter a Q&A where we will read your questions and answer and discuss these in the Q&A session. And finally, we will also do a summary, conclusion, and outlook for the for the upcoming webinars and VLCC as a whole, and availability and so on. So, and now, as the first, I want to introduce you to the first Slido question that has been published, or this is the first Slido poll. Please head over there and click on the alternative that fits. And I will leave the floor to Christian.
Yeah, thank you, Ludwig. As Ludwig said, my name is Christian Siegert. I'm the product manager of the HRL-VLCC and the consortium side of GAF. And in the beginning, I want to give a short overview of the whole HRL-VLCC product suite, and yeah, just an overview before we dive deeper into the actual forest product. The HRL-VLCC stands for the new high-resolution layers, vegetated land cover characteristics, and these products consist of harmonized products for forest, grassland, and the new cropland products. The HRL-VLCC continues and further densifies the well-established HRL time series for the forest and grassland products, and provides status layers with a spatial resolution of 10 meter, and the change layers for the grassland change and the forest change at its 20 meter spatial resolution. With the HRL-VLCC, we now move from a previous 3-yearly update cycle now to yearly updates for the crop products and the grassland products. These yearly updates starting in 2017, and for the forest products, the update starts beginning of 2018. All these products have pan-European coverage, and this means EA30A coverage, also including 5 French OC areas. It is foreseen that in an upcoming project phase, the United Kingdom will then be included as well, and when the United Kingdom will then be processed, the full VLCC time series will be processed then. Now, to give a short overview of the full product suite of the HRL-VLCC products. So at first we have the cropland products, which are new in this HRL iteration, and here the main status layers are the crop type status layers in a 10 meter spatial resolution with a minimum mapping unit of 0.25 hectare. And this product consists of 17 classes mapping the specific crop grown in these specific areas. The products are then also accompanied by additional cropping pattern products, which provide additional information on management practices on these cropping areas. And these can be categorized into the main crop, the bare soil, secondary crop, fallow land, and annual crop characteristics products. And these additional products provide further information, for example, of harvest dates and harvest events, crop emergence, presence of bare soil or secondary crops, and basically giving more information on management practices. And accompanying to these layers, there are then also additional expert layers available, the confidence layer, which provide further information on the plausibility of the respective classification. The second product line are the grassland products, and here we have the well-established grassland status layers, which is available in 10 meter and also in an aggregated 100 meter resolution. And there's also the established grassland change with 20 meter and an MMU, minimum mapping unit of 1 hectare, mapping the grassland change from 2018 to 2021. And within the grassland product series, we have now also new products. One would be the herbaceous cover layer, which maps not only the constant grassland cover, but also temporary grassland or herbaceous cover, and then giving further information on management practices as well. There are the grassland mowing events, which also have a spatial resolution of 10 meter and an MMU of 0.25 hectare, providing further information on management practices on these grassland areas. In addition, then there are also some expert layers providing the confidences and more information on the plausibility of these classifications, and then also the established plowing indicator, which highlights plowing events in the past years. And then last but not least, the forest product series consisting of the HRL, the dominant leaf type as main status layers available in 10 meter, as well as the tree cover density in 10 meter and 100 meter. Then the derived product forest type in 10 meter and 100 meter, as well as the forest change in 20 meter with an MMU of 1 hectare, mapping forest change between 2018 and 2021. Here are also various additional expert layers available, which would be the confidence layers again, and also leaf type density layers. The VLCC understands these forest products basically or mainly as any tree covered area, and doesn't follow specific forest definition. The only exception of that is the actual forest type products, which follows the FAO definition for forest, which will be explained later on. But all the other products basically map any tree covered area and not forest per any definition. To give a very basic overview of how these products are produced, the input data and the training data used for the production of the HRL-VLCC products are the Sentinel data, the Earth observation data that we use for producing these results, and those are combined with a large training database which contains data from in situ data from Lucas, for example, ancillary data sets coming from national data. Then we have the Green Land Cover Plus backbone data, which is also ingested in this database, as well as further Copernicus Land Monitoring Service data. So basically HRL data from previous iterations. Those are all compiled into one database, and then via cloud-based processing, there is a first initial classification done, which is called the base vegetation layer, which consists of 6 classes: herbaceous, broadleaf and coniferous trees crop, then an overlap class for tree crops, and the background class, basically consisting of all the remaining land cover classes. And this initial classification is then used as input for computing the actual forest, grassland, and cropland products, which then again use further Earth observation data as well as further ancillary data. So this will be the overview of the general production and input and training data for the HRL-VLCC products. And now we are looking a little bit more into detail for the actual forest product. And here we are starting with the first primary layer, the dominant leaf type, and then the derived change layer. And here we have as input the aforementioned training database, which then is combined with Sentinel-2 level 2A data. And these data are then used to train a model, and this classification model would be a temporal convolutional neural network. And before this training is done, there's also outlier detection and done in the sample revision to account and detect any outlier which would compromise the classification. Once the model is trained, we get as a result probabilities for the different leaf type for crop, herbaceous, the tree crops, and the background class. And these models are trained on several regional levels. So we use different models to account for the characteristics of the areas, different areas in Europe. Once the probabilities are available, these probabilities undergo then a multi-year consistency analysis and also a spatio-temporal smoothing, so that any unlikely class combinations within the 5 years is then smoothened, and those smoothened results then get intersected with the tree cover density layer, and then the dominant leaf type as a final first product is available, showing the areas which are covered with broadleafed or coniferous trees. During this multi-year consistency analysis, then there's also a tree cover change detection computed, where we basically compute the difference between the probabilities of the respective reference years. So this would be 2018 and 2021. And if this difference matches then a certain threshold, we consider these then as change, which would be then either loss or gain. And then this initial raw change map would then still undergo an MMU filtering to align with the technical specifications of the change map with the 1 hectare minimum mapping unit. And once this final tree cover presence share is then available, we can combine this layer then with the dominant leaf type, creating the dominant leaf type change. And here then we highlight any changes in the respective broadleaf or conifer covered tree areas, being it gain or loss. And these results are then internally quality checked and checked for artifacts and plausibility. And in case there are some errors or misclassifications observed, then the whole workflow starts from scratch until the results match the expectations. Then the next primary layer would be the tree cover density. And for the creation of this product, we also use the leaf type probabilities gained in the previous classification step. We combine these also with Sentinel-2 data and a training database with TCD, tree cover density samples from previous mapping campaigns. These data are then combined and used for a model training. And here, a different model is used to predict the tree cover density values. We use a gradient boosting tree model to produce the raw TCD maps. This is also done on a regional level to account for the different biogeographical characteristics of the regions across Europe. Once we got the raw products from 2018 to 2021, there's also then a cross calibration computed to smoothen out some outliers within the 4-year timeline. And once these time series has been smoothened, then there's an intersection done with the dominant leaf type, where then only the tree cover density shows the values for the actual tree covered areas. Once these final TCD is available, there's then again an internal quality check done for artifacts or misclassifications or highly unlikely values. And in case of any findings there, the process then is again started anew with some adaptations in the model process. Once these primary products are available, then there can also be some derived products be produced, and one would be the forest type, the only product that actually follows a forest definition. And here we are following the FAO definition for forest, which considers forests lands of more than 0.5 hectares with a tree canopy cover of more than 10%. And those areas should not be primarily under agricultural or urban land use. So on the right side, we see a summary of these criteria. So the forest type product shows only areas with a tree cover density of 10 to 100%, excludes area under agricultural use or an urban context, and has a minimum mapping unit of 0.5 hectare. In practice, this is done with an intersection of the primary status layers, dominant leaf type, and the tree cover density. And this intersection is then also done with the addition of Korean land cover data from 2018 and the HRL impervious density from 2018 to exclude the trees in urban context and under agricultural use. This intermediate product then still has some smaller patches, smaller than the required MMU. And in the last step, MMU filtering is done to remove these smaller tree-covered patches. And then the result is the forest type product in 10-meter resolution. Based on this 10-meter forest type product, there's then also a forest type 100-meter product available, which is derived through spatial aggregation from the 10-meter product. And this aggregation is basically done in two branches. The first branch during this aggregation is used to identify actual forest pixel, and forest pixel here mean that at least 50% of this 100-meter pixel has to be covered by a 10-meter forest pixel. This would be the first branch, and in the second branch, there is the leaf type occurrence counted. So in this example, we see in the background the leaf type occurrence for the coniferous trees, and in the the values here are quite high, especially in the upper left part, and in the front we have the cover for the broadleaf areas. And once this leaf type occurrence is calculated, we are computing a percentage cover of these leaf type occurrences, and those then get combined with the identified forest pixel, and in a rule-based overlay, then the final forest type in 100-meter resolution is created. This product follows the Korean land cover definition for broadleaf, coniferous, and mixed forest. And this means that, for example, broadleaf forest has to consists of 75% of broadleaf tree cover within these forest pixels, and vice versa then for coniferous. So at least 75% of this 100-meter pixel must be covered with coniferous or then respective broadleaf pixels to be considered as a broadleaf or coniferous pixel. And if none of these leaf types is dominating, then it is considered as a mixed forest pixel. Further derived products are the tree cover density in 100 meter and the leaf type density. The tree cover density 100 meter is an aggregation, and then the arithmetic mean density of the underlying 10-meter pixels is computed. And the broadleaf and coniferous cover densities are a spatial aggregation based on the 10-meter dominant leaf type product, where basically only the respective leaf type pixels get counted. Then there are further auxiliary products available. One would be the forest additional support layer, which is an intermediate product during the forest type production step. And this is basically the result of the intersection from the dominant leaf type with the Korean and the HRL imperviousness density. And this layer shows the trees that are predominantly used for agricultural practices and tree cover in urban context. Then there are 3 confidence layers available for the status layers. One would be the dominant leaf type, which shows a probability margin. This means there's a difference of the probabilities for the highest and second highest ranked leaf type calculated. Then the second confidence layer would be the confidence layer for the tree cover presence change. And here the change in total tree cover probabilities between the reference years, so 2018 and 2021, is calculated. And the third confidence layer would be for the tree cover density, which shows the standard deviation, which is computed from the total variance during the TCD modeling. Now, this was a rather quick overview of all the available products, and now we want to show a few of the examples of the products. And the first example would be the evolution of the HRL forest products from 2015 to 2021. And in this example, we see an area in Spain and the HRL dominant leaf type product in 2015, 2018, and 2021. In 2015, this was still produced with 20-meter resolution. In 2018, then there was this change to 10-meter with the Sentinel satellites. And in 2021, also Sentinel satellites are used, but a different classification approach is used. And in this Google Maps satellite image, we can see, especially in the left part, we have quite some dense forested or tree covered areas, and then in the right part there's more sparsely traveled, more sparse tree covered areas there. And in 2015 and 2018 we see that especially in the center part there are lots of these areas with the sparse tree cover not mapped, but yeah, with the permanent leaf type in 2021 produced during HRL-VLCC, we can see that these sparse tree covers also mapped, at least the majority of it is mapped, and also the quality and the detail of the classification is improved compared to the previous iterations, which can also be seen in the exclusion of the road that is crossing the image. Then a second example would be then the annual forest status layers. Here we can see a VHR image on the left side for 2018 and on the right side in 2021, showing forest stands in Western Germany, mixed forest stands with broadleaf and coniferous cover. And we see here the first primary product, the tree cover density, which shows in 2018 quite high values, but then due to drought-induced bark beetle infestation, a lot of the coniferous trees die and then finally get cut down. And we see in the tree cover density in 2018 there are still quite some high values. In 2019 we see some first decreases there, and then in 2020 and 2021 due to the large-scale clear cuts and dying of the coniferous trees, reduction of the tree cover density. And the dominant leaf type documents these changes quite good as well. So in 2018, basically all the forest areas are covered with broadleaf and coniferous tree stands, and then especially the coniferous part then is being reduced in 2019 and 2020 and 2021. Another example which shows the transition from tree cover mapping, which I mentioned before, to forest mapping is now shown here in this example near Genk in Belgium. So on the right side of this area, we have quite a lot of coniferous trees and broadleaf trees, and especially in the left part of this area, there's a lot of broadleaf trees belonging to some fruit tree plantations in the southwest of these areas. And the production of the forest type, this intermediate product, which was mentioned before, the forest additional support layer, shows here in this yellow brownish colors all the tree cover areas which are under agricultural use, and the orange and red parts show all the tree covered areas in urban context, which then get excluded during the forest type production. And then as you can see in the final product here, the forest type 100 meter for 2021, especially in the urban areas, there is no tree cover anymore included, and also in the southwestern parts the amount of broadleaf covered area is now greatly reduced. And one last example for now, documenting the tree cover loss due to fire damage in trees. Here we see on the right side the city of Athens surrounded by forests and tree cover in the north and in the western part, which is also covered quite well in the dominant leaf type of 2018. And here the tree cover density also shows quite high values, meaning dense tree stands in these darker green colors, and the yellowish coloring showing sparsely covered tree areas. And as you probably have noticed during the last years, these areas were damaged due to fires, which is then also documented here in the tree cover presence change product. So we see three major areas where the fire caused damage. So north of the city of Athens, and then also to the west we see areas where loss of tree cover occurred. And this can also be then mapped in the tree cover density of 2021. Here we see in the most left area, which was affected by the fires, that and not only a reduction of tree cover occurred, but we basically lost their actual tree cover in the central part, and the upper right part we see also a strong decrease in tree cover, but there's the tree cover present. Now, after showing these examples, I just want to briefly give an overview of the internal verification done after the processing. So in the processing steps, I said before, there's already internal QC done during the production process, but once the primary products are available, there's also an internal verification done by a team that's not involved in production at all. And the products that are internally verified by this independent team check the DLT product for 2018 and 2021, as well as the TCT for 2018 and 2021, and the forest change product. All these forest products need to meet the target accuracies of 90% in the user and producer's accuracy. And this verification is done based on a non-stratified, systematic, and random sampling approach based on a Lucas grid for the primary products, so for the dominant leaf type and the tree cover density. And for the verification of the change layer, there is a additional sampling performed to get statistical robust numbers and a decent amount of actual change samples. On the right side, you can see the distribution of these random sampling that were used for the internal verification, and the results of this verification exercise showed that the products meet the target accuracies, but there are some known limitations. For one, there are difficulties in the Mediterranean area, so here it's quite difficult to map these sparse tree-covered areas adequately, and in northern Scandinavia we have some problems with increased cloud cover. And although there are additional sampling performed for the change layers, there's still some uncertainty of the accuracy figures, especially regarding the potential omission of changes. Now to the part how to access the data for the HRL-VLCC. There are three primary methods foreseen to access the data. One would be API-based via the Harmonized Data Access HDA, which is hosted on VQ. The second option would be a tile map server with integrated MB tiles. And the third option would be over the official EA CLMS portal. With these three steps, we have quite a flexible approach for downloading the raw geospatial data, and also an easy way of visualizing these data in web applications. The API via the Harmonized Data Access allows the user to retrieve the specific EA tiles with corresponding metadata. The tile map server allows for some easy visualization and also easy embedding into other web applications. And the CLMS portal offers then a visually guided way for the user to download the data based on given AOIs. How would this look like then in practice? Via the HDA on VQ, the Harmonized Data Access, the user would draw a rectangle or any other shape for an area of interest, and then the user gets a product list with all the available products covering and intersecting the drawn AOI, together with further metadata for further filtering and downloading the data. The available filters would be different tiers and the different product types. The second way to access the data would be the visual data access via the tile map server. And here there are pre-selected sets of products converted into MB tiles and then hosted on a tile map server. So not all VLCC products will be available there, but mostly the primary status layers will be hosted then on this tile map server. And yeah, as mentioned before, these layers are highly versatile and can be then easily integrated into other web applications for an easy display. Then the last but not least option is the data access via the official EEL CLMS portal. And here the user has a quite simplified offer to access the data, being it in the data viewer or then also to download the actual data on some specific AOIs. The data are then provided with detailed product documentation, the user manual, and also the algorithm theoretical basis document is provided so users can read this documentation, get further information on the methods and product specifications. And all the products are delivered and provided with Inspire compliant metadata with each raster that is provided. So this would be all from my side for now, and I would hand over to Shaya to present the first use case. And before we start with the use case, I would like to remind you on the Slido questions, there is a new question available for you.
Thank you, Christian. I will share my screen. There we go. I'll wait a couple of seconds for everyone to complete the Slido question. Okay, so good afternoon, everyone. Thanks for having me, first of all. So my name is Shaya van Hout, and together with my two colleagues, Corine Driessen and Patrick Bogaert, who actually helped me to compile this presentation. I work at Statistics Netherlands, or the Central Bureau of Statistics in the Netherlands, in the team of environmental accounts. So today, I will show you a use case on the Copernicus tree cover density high resolution layer. And specifically, I will show you how we use the tree cover density layer to measure ecosystem condition in the Netherlands. So what exactly is ecosystem condition? Well, the SEA, or the System of Environmental Economic Accounting, specifies it as the quality of an ecosystem measured in terms of its abiotic and biotic characteristics. I'll get a laser pointer here. Here on this right side, we can actually see how the ecosystem condition fits into the system of ecosystem accounting. And we can see that together with the extent and condition, there is a flow of ecosystem services. But to simplify this part of condition, we can say that it shows the current state of ecosystems in terms of their physical and chemical state, their composition, their structure, their functioning, and their landscape elements. But why do we want to compile a condition account? So the EU regulation of environmental economic accounts recently expanded with ecosystem accounts, and they have based this on the SEA framework. It will actually become mandatory for reporting to Eurostat every 3 years, and the reference year will be set in 2024. With the first cycle of reporting actually anticipated in 2026. So the guidelines for the new indicators have only just been adopted, actually last week. So it will now proceed as an approved item to the council. This is just a formality. But basically, these regulations have been made by a dedicated task force on ecosystem accounting, and they've refined all these regulations. The Netherlands was also involved in this task force. So currently the proposed ecosystem condition accounts consist of the following indicators. So for settlements and other artificial areas, there is the indicator of green areas in cities and adjacent towns and suburbs. There's also the concentration of particulate matter that we measure. For both cropland and grassland, soil organic carbon stock in topsoil and the common farmland bird index will be measured. Then for forest and woodland, we actually have 3 indicators. So there will be dead wood, tree cover density, the common forest bird index, and that's all of them. And then finally for coastal beaches, dunes, and wetlands, we have the share of artificial impervious area cover. So what we could actually see here that was interesting is, of course, that there is this indicator called tree cover density. So therefore, we decided to have a look at the Copernicus tree cover density high resolution layer. So what does this layer show? Well, it shows the percentage of pixels covered by tree crowns. And when we did this analysis, there were only 3 layers available. So there was a layer for 2012, one for 2015, and then one for 2018. The first 2, so 2012 and 2015, they were available in the resolution of 20 meters and 100 meters. And the 2018 layer was available in 10 meters and 100 meters. So to actually create an indicator of tree cover density for the Netherlands, we set up a geospatial methodology using ArcPython, so a mix of ArcGIS and Python. And the data sources that we used were, of course, the Copernicus tree cover density layer and our own ecosystem type map, which also specifies production forests, natural forests, and other forests. So for each year, we then looked at the pixels from the Copernicus layer and overlapped them with the corresponding forest polygons from our ecosystem type map. Basically a bit like we can see here on the right. So this is the real world. And then here we would have the polygons from our ecosystem type map. And this would be the Copernicus tree cover density layer. So just for illustration, this is our ecosystem type map. In here, this green blob, that is the Veluwe, as we call it. And that is where most of our forest is in the Netherlands. You can not really read it here because the legend is in Dutch. But basically the darkest green here is production forest, and the slightly lighter green is natural forest. So there's kind of a mix in here. So after we overlaid the ecosystem type map and the tree cover density layer, and then we actually summed the pixel values for each forest type and divided them by the number of pixels to get the average percentage of tree cover density. So I actually try to explain this visually. So here we would have for tree cover density pixels, of which 3 actually contain forest. So that's why this one has a 0. One pixel has 60% coverage, one has 80, and one has 85. The 60% overlaps with a polygon of natural forest, and the 80 and 85 overlap with a polygon of production forest. Well, what we then have to do, because the production forest has 2 pixels, well, we have to add them and then divide them by 2 because there are obviously 2 pixels. So then this would be the result. Obviously, this is a very simplified version. If you have to do this for all of the Netherlands, it's a bit more complicated. Yeah, so then what can we actually see from the results? Well, we can actually see that over time, tree cover density is quite stable. You could maybe argue that there is a slight increase between 2012 and 2015, but then in 2018, oh, my mouse is stuck. Then in 2018, the tree cover density actually goes down again. However, these differences are probably actually due to the fact that the 2018 layer has a higher resolution. So it's not really comparable to the 2012 and the 2015 layers. Besides that, the trend only has 3 data points, which probably isn't enough to really identify a trend. So we would probably need a few more data points to actually see a clear trend out of this result. But another result that we can identify from this graph is that forest type really matters. So we can see here that the pink line, that is production forest. And they actually have the highest tree cover density, which is actually quite logical, given the fact that they are planted close to each other to produce a high yield per area. And besides that, production forests are usually planted with high yield species that grow quickly and can produce large volumes of timber or biomass in a shorter time frame. These species often have denser growth habits than mixed natural forest, leading to a more uniform and crowded canopy. The natural forests are actually slightly less dense, which we can actually see here. This is the orange line. So the green line is all 3 together, but the orange line is basically almost the same. And then we also have the other forests, which are a lot less dense. And this is probably because these are just small forest patches scattered around the country. So our conclusion from this is that it's probably best to focus on the natural forests, particularly because production forests have artificially high uniform densities due to the management practices, which don't really reflect the true ecosystem health, diversity, and resilience. And natural forests, with their structural complexity and biodiversity, provide a more accurate measure of ecological condition. So what have we learned from this case study? Well, we will definitely need this layer in order to comply to future mandatory international statistics. However, the resolutions and methods used to create these layers must be the same for multiple years, because it is difficult to compare between years if the specifications, like the resolution, changes. The indicator itself is quite hard to interpret in the Netherlands, actually, because open forests are actually more diverse than the denser forests here. So higher is not always better. So we need to be really careful how we interpret the indicator. However, we do think that the high resolution tree cover density layer is very easy to use. There is very good documentation on how these layers have been compiled. And we've actually just been promised before this that there are a lot of new updates coming, and they all use the same methods. actually all the issues that I noticed here have all been resolved. And that's it. So I think there's another Slido question. And then we can go on to the next case study.
Thank you very much, Aya. Yes, we now have Stefano, who will share his screen, and please, the floor is yours.
See, just sharing my screen. Good afternoon to all of you. Just confirmations that you can see my screen actually.
Yes, and
Okay, I'm turning it to full screen right now. Just can you confirm
Perfect.
this, Ludwig? Thank you so much. So I'm checking timings, that it's important. So thank you so much for having invited me, first of all, and really glad to participate at that seminar. My name is Stefano Salata. I couldn't be immediately online, so I don't know if you introduced already myself, but a couple of words. I'm a researcher on the Department of Architecture and Urban Studies here in Politecnico di Milano. And my research passion, let's say, it's mostly concerning digital mapping, ecosystem service modeling, and how to measure land use change effects on natural elements and natural capital as well. So the title of this presentation is how to design urban green infra using basically open source data. And that's mainly my main objective also of research when I'm going to deal with students that wants to learn on how to mix up different kind of knowledge in order to support environmental planning. Sorry. Or when I have to deal with public administrations that asked us as a department here to develop their own plans about land use change, or when they want to create green corridors or develop green infra as well. So briefly, I won't repeat what Shaya was mentioning about ecosystem services, but I think that's a key, because also from my side, from my experience, the product that you produce are basically really influencing the way we are going to address this concept of having multifunctional green infra, which means that basically through a set of indicators, you can build up a set of knowledge and creating this kind of environment to model ecosystems, and then understanding what is the, let's say, how they goes on hand, or when they are clashing each other, and understanding, spatially speaking, what are the hotspot where we have concentration of multifunctional values, or on the contrary, where do we have to make interventions in order to maximize their benefit. So I'm sorry to take a bit of time for this introduction, but basically, I used to play with models because models allows urban planners to understand where things happens. And basically, I'm putting invest, but there are a lot of tools that nowadays you can use to map ecosystem services. But the link with the products is that if they are white box tools, then you can mix up and using these kind of high resolution layers in order to feed the models and check it out how much the outputs that you can get are reliable according to the kind of inputs that you can give to them. And I think that layers that are released that we are talking about are especially the tree cover density, but even imperviousness are those that I mostly use during my exercise or during my commitments within the public administration. So the first point that I wanted to touch with that presentation is this one concerning teaching, because I used to have certain courses. That one was an environmental planning. That was the title on the bachelor degree on urban planning. I was teaching in Izmir, Turkey at that time, but at that moment there were no data about the catchment that I wanted to play with the students, and I was worried about the possibility to get certain kind of let's say results on the studio, because you see, two models were dedicated at making certain kind of spatial analysis, which is quite more simple in catchments where you have a lot of digital information, but it's much more complicated in Turkey where you don't have that much redundancy of data. So in that case, I was again using land use, land cover, or the tree cover density and imperviousness as the main layers. And I was giving to students certain tiles, and then I let students work to play with ecosystem modeling and so on. So the idea was to create a kind of flow for all the class where groups of students were self-organizing, inserting subcatchments, and they were overlaying simply these layers, so impervious, tree cover density, and then habitat quality. And then through the superimposition of this layer, they were making several composite maps. That's just one of the results that we get. That's a habitat degradation map in the catchment of, that's just a part of Izmir province. It's the northwestern side, but this is just to let you know how much in detail we can get this assessment. It was enough to understand exactly how much you can get into the urbanized land and how is the increase on the degradation of the habitats through the linear distance that you can get from a road or a motorway or whatever kind of land use that is going to create an anthropic effect to the natural habitat. And within this kind of set of tools, we were able to receive even a formal commitment when I was still in Turkey for designing a green infra. That's another neighborhood, but we use the same package of knowledge, let's say, so dealing with imperviousness, tree cover density, habitat quality as the main input to create an overlay with them. Even though this is a hand-drawn sketch, but this green infra has been modeled by using these high-resolution layers, and we were able even to understand what is the average, let's say, environmental capacity of the public space in Karşıyaka. This is the municipality of Karşıyaka. So we were able to even understand where to prioritize certain kind of interventions to, for example, create more nature-based solution. You have to know that Izmir is a super dense catchment. The average imperviousness rates in the central part of the city, I'm talking about the average, is about 95 to 97%. So it's really tough to work there in order to create ecological continuity and so on. Still, within that knowledge, we were able to work with minor intervention. So the second case that I'm going to present is not an exercise made by students, but that's a real commitment that we have here in Milano. The municipality is a small one. Its name is Ambivere, and but more or less the approach that I was having within my research group here in the lab is the same. So having multiple map of ecosystem, here we have infiltration capacity, habitat quality, erosion control, and accessibility to the habitat. And all of them were basically composed again using digital elevation model, land use, land cover, imperviousness degree, forest, tree cover density, basically. And we were working again within the superimposition with the local land use plan, and we were able to create the first, let's say, frame of this composite green infrastructure system. The idea of the public administration was, or made better than the idea, their goal was to bring more natural elements into the city. So what you see, the big stain of green in the southwestern part here is a hill that is touching the settlement system on the eastern side. And their idea was to create more corridors in order to extend the density of trees within the urban catchment. So increasing connections probably was their goal. And we were able to divide different kind of actions just using the models and suggest them where to prioritize again intervention to create this corridor or path of accessibility to the hill. And then another one that seems to be a bit far away from the products that we were talking about, because in that case, I want to show you how recently I was able even to integrate Sentinel product with high resolution layers. Again, I was dealing for a research that has been carried on my department in Mykolaiv in Ukraine. Here, the city is under attack right now, so still having data is really tough, and I couldn't have any kind of digital data. So the first things that I made was recreate a bit of land use, land cover through a just composition of the bands by Sentinel. And then I was producing a build-up footprint by just making a supervised classification sampling. But then once I was just selecting the area with high permeability, then I was superimposing the tree cover density layer because I wanted to have a kind of layer, which allows me to understand where I have permeability, what is, let's say, the healthy status of or the density of the vegetation into the pervious land. And that was super fruitful because I was able even to understand into the dense catchment where do we have continuity of tree covers. And that was really important because in the end, the administration asked us to give guidelines for the next master plan for rebuilding back the city once the conflict will end up. Of course, we are dealing with a lot of uncertainty here, and still the conflict is ongoing. Then we made a step ahead, and I did more or less the same procedure that I used to play, and I was telling you previously. So I was using this as an input for the habitat quality and decay. And then a second model, which is called stormwater management, where again, using tree cover density and imperviousness layer, you can feed the model of the percolation. It's hydraulic conductibility, basically. And then what I get in the end was having two maps where I call them priority of interventions, because where I have few retention and where I have a lot of decay, then it means that probably the green infra needs to select certain features and say which kind of actions do we want to prioritize in order to create more ecological continuity and create a more green and accessible mycolife in the next future. I'm going to the last two slides now. The last, but probably one of the most important work that I'm still carrying on is the land use plan of Varese, which is coordinated by the scientific coordination of Professor Arcidiacono, which leads my lab here. And again, here, what I want you to know is that the public administration wanted us to understand exactly what is the state of art, let's say, in terms of canopy coverage in the city. Varese is placed right below the lake area, we call it in Lombardy. So it's a city which is labeled as a città giardino, a garden city. And we were checking out, empirically speaking, how do they call this città giardino, if it's true, first of all. And we were making a kind of average quantity of tree cover density per each neighborhood. We were discovering that the average tree cover density is at 38%. And we were making even a classification of what is the contribution of each single neighborhoods in order to, again, say, in the next land use plan, which neighborhoods do need to be treated by more planting, for example, trees, or creating more ecological corridors and permeable space. And we set even a threshold, understanding that the average, the per capita vegetation cover is about 1,200 square meters per citizen. So now our commitment with them is to set, let's say, the goal, starting from this knowledge and then saying what the next land use plan within the new green infra can achieve. But if we don't set this kind of baseline, then it's really hard, even for land use planning, to understand where do we want to go and if we are able to reach the target. So from my side, I think it's all. I think I'm in time, and I just want to remember that there will be another thing, another pool in the system.
Thank you very much, Stefano. Very interesting use of the products and the use cases there. Okay, yes. That's all for the presentations. As Stefano said, there's the final poll presented, asking of what type of applications are you using the products for. And now we go back to Christian, who will share the screen for the final part of the webinar, where we will first enter the Q&A session. Let's see. Okay. There we go. Okay, so for this session, I will follow the list of questions that you posted on the Slido, and also voted for. So I will go in the priority order here, and delegate questions to the panelists as they come in. the first and top question is, how accurate are the maps? How is the error estimate calculated? And what is the reference data? And this I want to maybe Christian can come in and explain a bit on the validation that we do. I also first point to the previous webinar where we went through a bit on the production or internal validation that is being performed, but also the external validation. And when the product manual, user manual, and also the external validation report for many of these products is published eventually, you will have a good insights in this. But please, Christian.
Yeah, so basically what I've shown in the map with the sampling design, there is these random sample points that then got checked with the products that we produced. And in the first blind approach, basically the product is only then used with high resolution data, and then as reference data. Then in the plausibility checks, there's then also VHR data used and additional data. This would be then existing CLMS products, but mainly then the VHR products, especially for the forest products, the dominant leaf type there, the VHR is basically sufficient to make a decision there if the classification of broadleafed or coniferous is correct. The verification for the TCD is a little bit more elaborate. So there is not only the specific pixel considered, but during this verification, there is like the area to be checked increased. So there is a grid created around the sample point that is checked, and then there are 25 separate points created, and out of these 25 points, then that is the mean value basically computed and then compared to the actual results. But yeah, this will then also be explained in more detail in the documentation that is provided then once the product gets published.
Thank you very much. Okay, so continue here. The second question, could you share details on a peer-reviewed publication that describes the products and presents the methodology? Not a report, but a peer-reviewed publication. We got a similar question in the previous webinar. So with the full portfolio of the VLCC, the forest, the grassland, and the crop types, we are publishing a algorithm theoretical basis document, the ATBD, and this is going into details on the models that are used for each of the product suits. And here you will also find references to scientific literature that have we're basing our methodologies on. So please keep your eyes out for that when it goes live. And then next question is on the forest type. How do you determine agricultural use? I leave this for Christian or one of his colleagues who are in the panel as well.
Okay, then maybe I start. So concerning the forest type, as I've shown before, there are these ancillary data used to define these agricultural use. So in this case, it would be the Korean data from 2018, which has several respective classes mapping olive trees and fruit trees, fruit tree plantations, which is then used for the intersection to exclude these areas in the forest type product. Yeah. In general, for the VLCC, the discrimination between agricultural areas and herbaceous cover, then this is following also the CLC plus definition that there has to be at least one land cover change throughout the year. So in this initial classification that I mentioned in the beginning, we consider agricultural area all as all areas that have one land cover change within the year. That's then basically a harvesting event, leaving bare soil, or a plowing event. I hope answers the question.
Exactly, and to refresh or maybe introduce for participants who are not aware, the Korean land cover is a long flagship CLMS Copernicus Land Monitoring Service product, which is a kind of a one-of-a-kind land cover and land use mapping. It's a manual interpretation performed by member states. So each member state is performing the mapping every 6 years, and so that is how we then receive and can base such land use determinations on. And then just jumping a question, but we'll go back to it because related to this, there's a question: is the forest additional support layer, forest additional definition support layer is the full name, FADSL, available? If so, where can it be downloaded? So this additional support layer is including this information on how the tree cover is classified for the filtering of the forest type. So it's an intermediate layer for the forest type processing, and this layer is also being will be available for the reference years where forest type is derived. So remember, forest type is derived on a 3-year cycle. So we will have a 18 and 21 forest type in this batch, and then along that we will have a FADSL, forest additional definition support layer, for 18 and 21 as well. Okay, and it refers to where it gets the information from Korean or from imperviousness density and so on. So it's made available for users to be able to get insight into that filtering process. Okay, back to, yes, are detailed documentations available to describe the products and the methodology used to produce them? Yes, this is coming. In both the product user manual on a more overview basis per product suit, there will be one for the forest, one for the grassland, and one for the crop types. And then there will be one long ATBD for the full VLCC, the Vegetated Land Cover Characteristics production system and methodologies, as I mentioned before. From the tree cover to forest mapping, how do you define the tree stands belong to urban areas? Yeah, can you expand on this as well, Christian? You partly mentioned it earlier.
Yeah, so in this intersection mentioned earlier, there are these Korean data sets used, as well as the HRL imperviousness density. And this density, or the urban context, is then including all pixels and areas where the impervious density has at least 1%. And then also in the Korean class, there are some specific classes for sealed and basically urban areas. And the combination of these Korean classes with the HRL imperviousness density is then used to exclude these urban areas. And in this FADSL product, then there are these specific classes. So in the examples I've shown, there was this more orange part and this more reddish part. And then in the FADSL, you can see which area got excluded because it's an oversection with the Korean data, or if it's due to the intersection and the overlay with the HRL imperviousness data. So this is then basically shown in the FADSL.
Yep. Exactly. Thank you again. And then further, another question: will the tree cover in urban context be comparable with the urban atlas tree layer? That's a really good question. Yes and no. It depends on the accuracies and the comparability that is to be achieved. The urban atlas tree layer is based on a different sensors and on the kind of what we call the priority area monitoring. It's based on the Copernicus contribution missions very high resolution coverages that are made available every third year. And the street tree layer in Urban Atlas is nowadays derived from the product which is called the small woody features, or the small landscape features, which is mapping the linear elements, woody elements in all over Europe. So similar methodologies are performed for the urban areas as well. And so that is a different production line. So for the tree cover density or dominant leaf type that we derive here, they are derived from the sentinels, right? So there is, of course, a comparability, but the street tree layer will be based on a higher resolution data and probably catch more single trees and so on in the urban landscape. However, on the other note, they are produced on a 3-year cycle, while the tree cover density and dominant leaf type are produced on an annual cycle. So probably if urban trees are your study area, your interest, then I think a combination of both is a good one. But they do provide different data accuracies and temporal resolution. The street tree layer is on a 5-meter resolution, but based on VHR imagery from 2 to 4 meter resolution. Okay. Is there a plan to extend the temporal availability of the data sets beyond 2021? Yes. So now with what we're launching here is the annual production of VLCC, again, the forest, grassland, and crop types. And the first batch, we call it, is the 17 or 18 in the forest case, the tree cover case, for annually up to 21. That's the first batch, and we're already up and running with a second phase of this production, which is the 22 and 23, trying to catch up into the timeliness that we have as our ambition. And we are also defining currently the production of the 24 reference year, which is still to commence. So expect 22, 23 to be published around quarter 3 of next year, and then 24 to be published around quarter 1 of 26. We expect eventually to reach a 12-month production timeline, and then we probably will increase that ambition even further, but we'll see what is possible. Okay, next question. Do you have pre-analysis of which accuracy you should achieve with products for use in post-classification change detection? I'll leave this again to you, Christian, to expand on the accuracy, the quality assurance, and what we define and how we validate it.
This pre-analysis, I'm not sure if this was done in the initial phase of the project. Maybe my colleague Andre Stumpf could comment on this, how these thresholds.
I can try to reply to that. Yeah. So I mean so we have a 3 change product which was presented, which covers a 3-year period, right? And so the yearly status layers, they are consistent with the change layer. So if where the change layer has an accuracy of 80-90%, you will see exactly the same changes in the status layer, so they kind of have the same accuracy. Having this said, so the change layers have an MMU of 1 hectare, which is not in the status layer. So if you would go and subtract the yearly status layers, you would see some changes, additional changes below the MMU, which are not represented in the change layers. And typically, the smaller the changes get, the more difficult it is. So the changes which are not in the change layer, because they are below the MMU, would be less accurate. Yeah, how accurate exactly? We haven't assessed that at this level of detail. Yeah. I hope that answers the question. Yeah.
Yeah, thank you very much. Okay, and then I have a last question, and it's for, I hope you still hear me. I had to change my headphones, running out of battery. The last question is for Stefano, and it reads like this. In the city management plans in Italy, do you have specific minimum percentage of urban green per type of functional use?
Yeah, thanks for asking. That's a good question, because actually we don't have a kind of generic minimum percentage for all the green. It means that we have a percentage for just for the public green space, which it's an old law that we have, but still in place, which says that for the residential area, for each new theoretical inhabitants that we want to place on the new transformation site, we need to locate at least 15 square meters of public green space. Without saying, I mean, regardless of the typology of green, if it's covered by trees or not, but it should be given to the public administration for just having permeable, recreational space. As for the other uses, the rule that we have, it's a planning rule, I mean, not an environmental one, says that for the commercial or for the industrial surface, I mean, new development or regeneration, we have to give the 50% of the gross plot surface during urban transformation for green, again, areas. But again, this is regardless on the typology of green. It means public greens, but there are many, many typology of different. You can have public, fully equipped areas, those with benches and so on, others completely, let's say, grasslands with no trees and so on. So what we try to do actually in planning is to find out a way to, let's say, upgrade a bit more, saying what is the quality of that green instead of providing just a minimum quantity, because that's the key of urban planning actually. I hope I have answered it, by the way.
Yeah, thank you very much. Indeed, a good question. Then that was all for the questions posted. Thank you very much for the interest and good questions. So we can move on and finish up the webinar. We're closing into 3:30. So Christian, can you switch the slide to the conclusions? Yes, thank you. So we have seen today seamless on the VLCC forest portfolio, providing seamless continuation of the HRL forest, which have been produced in 3-year cycles from 12, 15 to 18, and now moving to annual updates. It's providing both change layers and a forest type definition on a 3-year cycle. The forest and the tree cover and forest products are in general with very high accuracy and spatial temporal consistency with other HRL-VLCC products due to being produced in the same product system, but also with other CLMS harmonization and interoperability with other CLMS products as well. For example, the HRL imperviousness, the non-vegetated part of the classification, land cover classification. It's addressing various environmental needs and such as the proposed European Forest Monitoring Law and also the LULUCF regulation. We've also seen 2 very interesting use cases visualizing how to apply data and to derive interesting conclusions and statistics from the land cover for a tree covered land cover. And then the next slide, I think we have just the outlook. We have the upcoming VLCC webinars. Make sure that you have registered for these as well. In the next one, we're gonna, in a similar way, dive into the grasslands on the 19th of November, same time, from 2 to 3:30. And then on 10th December, we're going to finalize this series with the crop types and the cropping pattern products. And we're also going to hear, in both of these, we're going to hear some interesting use cases The last one there on 10th of December. So thank you very much for joining. I would like to say thank you to our panelists. Thank you very much for your presentations, and to participants for all your good questions. And I hope to see you next time then in the Grassland webinar in 3 weeks' time. Thanks.
Thanks, everyone. Bye-bye.
Bye-bye.